Okay, so now I'm going to try to derive some of the equations that we are using in thermodynamics. So first, let's start off with the incompressible. Using the fundamental relation of T_ds equals to du plus P dv. For incompressible substance, we know that T_ds equals to du, and we can drop the dv because incompressible, there's really not much change in the specific volume. So we can write ds is equals to du over t, and this du over t is nothing but just du by dt, dt by t, dt by t. It's the same thing, but we know that du by dt is actually equals to the specific heat capacity at the volume, so otherwise it's known as Cv. So now that we have this relation, we can try to integrate on both sides. Integrating on both sides, we'll realize that we have Cv ln T2 over T1. So this is the entropy change for incompressible substance. Next, we'll move on to for compressible substance, which is also known as ideal gas. So for compressible substance, we can either use this equation 1, or we can manipulate it using the H equals to U plus PV equation. So in finitesimal scale, we have So I want to rewrite this carefully. dH equals to du plus v dp plus p dv. Okay, let me erase this. Then, if we manipulate this again, we can realize that du plus p dv is equals to the right hand side of the equation 1. So we can rewrite TdS equation as TdS equals to dH minus v dp. Okay, so we can further simplify this equation by writing as ds equals to dH over t minus v dp over t. Now realize that this dH over t, we can further simplify it as, or we can rewrite it as dH by dt and dt by t. dH by dt is really nothing but just specific heat capacity at constant pressure, Cp. Cp equals to dH by dt, and Cv equals to du by dt. So on an ideal gas basis, we know that the relation of PV equals to MRT applies. So applying this, we can realize that V over T is equals to MR over P. Since this is on a specific ratio, we are going to drop the M, and we can rewrite it as V over T equals to R over P. So applying it to this equation, we have Cp dt by T minus, so we realize there's a V over T right here. There's a V over T right here. So we're going to rewrite this as R dP by P. And then we can integrate on both sides. And we will get delta S equals to Cp ln T2 by T1 minus R ln P2 over P1. And so this is the equation that we'll get, equation number 2. It's the same thing. Now, what about the other side? if we are going to use internal energy. We can also use the same thing. Okay, so firstly we have ds equals to du by t plus p over t dv. Again, from the specific heat capacity ratio, a specific heat capacity of a constant volume, so we have C du equals to dt times dt over d over t. So this thing is actually your CV. Okay, so using the ideal gas equation, we can realize that P over T is actually equals to R over V. So this one is actually can be written as R over V. So if you want to rewrite it in a more formal way, CV dt by T plus R over R dV over V. Then we integrate on both sides, right? We will get delta S equals to CV ln T2 over T1 plus R ln V2 over V1, which is the same as the equation 1 we get here. So I will not rewrite this. So these are the two equations that you can use for ideal gas or any incompressible. Okay, so now I want to talk about reversible. So for reversible process, we have delta Q equals to TdS, right? So we can rewrite this as okay. So we have two fundamental relations for reversible process. First is del Q equals to TdS, and the second one is the first law of thermodynamics, which is conservation of energy. So using these two equations, we know that TdS minus del Q equals to dH. And we know that from the ideal gas here, this part here, we have initially derived the function that TdS equals to dH minus VdP. So we're gonna impose it here, dH minus VdP minus delta W equals to dH. So straight away we can see that this dH and dH can cancel away, and negative delta Q del W is equals to VdP. Hence, once we integrate on both sides, straight away we can find out that the work done can be written as V P2 minus P1.